Hi there, and welcome back to my Precalculus video series, where my goal is simple: to make Precalculus make sense. In the last lesson, we explored how real numbers live on a number line. If you missed it, you can find that video right here. Today, we're taking that understanding to the next level by grouping numbers into sets and learning how to express entire intervals on the real line. By the end of this lesson, you'll be able to 1. Identify and write sets using proper notation. 2. Use set builder and interval notation correctly. 3. Understand unions, intersections, and the empty set. 4. Graph intervals on the number line. And 5. Explain why open intervals don't have smallest or largest values. Thank you for being here. Now let's get started. Let's say you want to describe all even numbers less than 10. Do you write them all out? And what if that list goes on forever? That's where sets and intervals come in. They help us describe groups of numbers in clean and compact ways. Now, what is a set? A set is just a collection of objects. And in math, those objects are usually numbers. We use braces to list them. For example, let's define set B. This is a set of even numbers less than 10. So you see we have 2, 4, 6, 8. Each of the entries are what we call elements. So we say 2 is an element of B, 4 is an element of set B, 6 is an element of set B, and 8 is an element of set B. If we want to describe this more generally, we can use set builder notation. It looks like this. This reads, B is the set of all x such that x is even and x is between 0 and 10. I know I had to write a little bit on the edge here, but this just says x is between 0 and 10, and then I finally closed off this initial brace over here on the edge. Now let's talk about set membership. We use this symbol to say something is in a set. This is the symbol of set membership, and it means is an element of. The same symbol with a cross on it means is not an element of. For example, 4 is an element of set B, because here above, set B includes the elements 2, 4, 6, and 8, and 4 is an element of that set B. If I wanted to consider the number 9, it is not an element of set B. Some sets already have special symbols. These are fundamental, so it's good to get familiar with them. We have a capital N for the natural numbers. We have a capital Z for the integers. We have a Q for the rational numbers, and we have the capital R for the real numbers, which can just be all numbers on the number line. Can you read what I'm writing here? This just says that pi is not an integer. Which makes sense, right? Because in lesson 1, we learned that pi is an irrational number. And if these symbols for these special sets of numbers is not familiar to you, you can check out my very first lesson of this Precalculus series right here. Here is a quick check. Is 7 an element of this set? The answer is yes. In the set, we have 1, 3, 5, 7, and 9, and so 7 is an element of this set. How about this? Is this true or false? This is a false statement because 6 is a natural number. Natural numbers start from 1 and go on until positive infinity, and 6 is included in that set of numbers. So this is false. Now let's take two sets and see how they can combine. Let's define set A and set C. A is the set that includes the following elements, and set C is the set that includes the following elements. What happens if we combine them? This is called a union. So a union is easy to remember because its symbol is already a U shape. And so what a union does is that it includes everything in set A or in set C or both. So if I find the union of set A and C, I'm going to include everything. Set A has a 1. Does set C have it? No, it doesn't matter. I'm writing down everything we have. Set A has a 2. It doesn't matter if set C has it. So I have a 2. I have a 3 that's shared between A and C. That's okay. They both share a 3. I have a 4 in set C. That doesn't matter if A doesn't have it. I include it. I have a 5 in both set A and C. So I just include it. And then I have a 6 in set C. So I include it. It's everything in both sets. Now, what if we want to find elements that they have in common? That is an intersection. If I wanted to find the intersection of sets A and C, I'm looking for what they have in common. So I start off with 1. A has 1, C does not, so they don't have that in common. 2 is an element of set A, it is not in set C, so that's not included in the intersection. 3 they both have in common, so I can include it in the intersection. 4 is only an element in set C, so it is not included in the intersection. 5 is present in both sets A and C, so it is included in the intersection. And 6 is not present in both sets. And this is the intersection of sets A and C. And finally, if two sets share nothing, their intersection is called the empty set, which we write using this symbol. Here's a quick example of the empty set. If I want to find the intersection of the set containing the elements 1 and 2 and the set containing the elements 3 and 4, well, I'm looking for what they have in common. Well, the first set only has 1 and 2. The second set only has 3 and 4. They have nothing in common. So the answer is the empty set, which is like a 0 with a cross through it. Instead of listing numbers one by one, like in a set, we sometimes want to describe all the real numbers between 2 points. This is where intervals come in. They represent a continuous range of numbers. For example, let's look at a few common interval notations. The open interval 1, 5 means all numbers greater than 1 and less than 5. Let's draw an open interval. When we're drawing intervals, we use a number line, like we spoke about in the last video. Since we're dealing with an open interval, it is written using parentheses. These parentheses indicate two things: that at the points 1 and 5, we get open circles. And these open circles indicate that the endpoints are excluded from the interval. So the open interval 1 to 5 is all numbers greater than 1 and less than 5. However, it does not include the values 1 and 5. So if you had to pick a number in this interval, you cannot pick 1 and you cannot pick 5. And this is a huge key idea for you not to forget. The next type is a closed interval. Let's take a look at the closed interval 1, 5. This means all numbers greater than or equal to 1 and less than or equal to 5. The important thing to remember about closed intervals is that closed intervals include the endpoints. Geometrically, our line segment would look like this. Now, because we're dealing with a closed interval, like we just said, closed intervals include the endpoints. So in order to show this, instead of using an open circle, we use a closed one, or a filled circle at both of the endpoints. And again, intervals describe all real numbers between 2 points. And so we describe all possible or all values included in this interval with a solid line. So if you had to pick a number between this closed interval, you can include 1. You could choose 1 as an option. And now you can include 5 as an option. Whereas in the open interval, you could not. You could choose a number like 4.9 or 4.99 or 4.999 with 100 nines at the end of it. But you can never choose 5. You can get as infinitely close to 5, but you cannot choose 5. Whereas here, there's no problem with the closed interval. And the biggest difference is that open intervals use parentheses and closed intervals use square brackets. Square brackets indicate endpoints are included. Now we can have a mix between open and closed intervals. Let's look at this interval, 2, 7. Notice the left-hand side has a square bracket and the right-hand side has a parentheses. This should automatically mean that the endpoint 2 is included because the square bracket is there, but the endpoint 7 is not included because of the parentheses. So what this means is all numbers greater than or equal to 2, but less than 7. If we draw its graph, it'll look a little something like this. So because we have a square bracket at 2, we're going to have a filled circle. And because we have a parentheses at 7, it's going to be an open circle. And intervals include all real numbers between those 2 points. Now we can take a look at these 3 examples that we've done and write them using set builder notation. In this case, we can describe this interval as all values of x such that x is greater than or equal to 2, but it's less than 7. Notice the choice of inequalities that I used. If it's a square bracket, I use my greater than or equal to symbol. X is greater than or equal to 2, and it can be equal because we have a closed circle. But it has to be less than 7, but not equal to, and that's symbolized by the open circle. Let's go back to our other examples. I can write this as the values of x such that x is greater than 1, but less than 5. And for our closed interval, this interval includes all values of x such that x is greater than or equal to 1, but less than or equal to 5. Next, we're going to list the possible types of intervals that you can encounter. The first is an open interval with the endpoints a and b. And so the set description would look like this. The values of x that are included in this set are the ones that are greater than a but less than b. Next is this closed interval. Since we have square brackets, the values of the endpoints are included, so we fill them with filled circles, and we include every single real number between those two. Next, we have a half open, half closed. Since I have a square bracket at a, that endpoint is included. Since I have a parenthesis at b, that is not included, so I'm going to get a open circle. And the values of x are everything greater than or equal to a, but less than b. Next, we have another half open, half closed interval. Since I have a parenthesis at a, letter a is not included. Since I have the square bracket at b, that is included, so it gets a closed circle. And the numbers are everything strictly greater than a, but less than or equal to b. Next, we're seeing our first example of an infinite interval. At a, we have a parenthesis, so it's not included. Other end is infinity, which has no end. So that means that the values begins at a, but does not include a, and extends all the way to infinity. So it continues going on forever. In this next one, we have a square bracket at a, so now we can include a. So the smallest value we could take is the value at a, and it extends all the way into infinity because the values of x are greater than or equal to a. In this next interval, the numbers begin at negative infinity, so we include all numbers infinitely to the left, and they stop right before the value at b. Now if you notice, we have a parenthesis, so the value of b is not included in this set, but everything right before it is all the way towards the left. In this next interval, the values of x extend all the way from negative infinity and extend all the way to b. And since we have a square bracket, this value of b is included. And so the values of x are everything less than or equal to b. And this last example extends from negative infinity all the way to positive infinity. And so this is what we know as all real numbers, or the set of real numbers. And it includes the entire number line, stretching from negative infinity all the way to positive infinity. Now it's your turn. Using what we've just talked about, write the inequality x is greater than or equal to -2 in interval notation and sketch its graph on a number line. Pause the video here for a few moments and we'll talk about the solution to it right now. Okay, so let's talk about what it means to be greater than or equal to -2. Well, this means if you want to imagine a number line, if this is -2, this would be -1, this would be our 0. Greater is towards the right, which is towards 0. And so this means -2 is our smallest number, but since we're equal to it, we need to include a square bracket. And if x just needs to be greater than or equal to it, that extends all the way to infinity, which means that I can draw a closed circle at -2 and extend all values of x infinitely towards the right. And you should note that whenever we use infinity, you always need to use a parentheses. Now let's talk about what it means to have no smallest or largest number. Here's something to think about to deepen your understanding of this. What's the smallest number in the interval 0, 1? What's the smallest number you can think of? Now, if we draw it out, it's going to look like this. This is 0. Let's call this 1. Since it's an open interval, the values of 0 and 1 are not included, but everything in between is. You might think 0.1 or maybe 0.01, but there's always going to be a smaller number still inside the interval. You can pick 0.00001 if you wanted to, which is even smaller, and it's still in this interval. But the problem is that this process can go on forever. And that's the unique thing about open intervals. They do not have a smallest or a largest number, even though they have clear boundaries. The boundary 0 at the lowest end and 1 at the highest end. Now let's do a few examples involving infinite intervals. Let's consider the infinite interval, -infinity, 3. Using what we've talked about on this left-hand side, we know that its graph is going to extend all the way to the left, infinitely to the left. But it's going to have a boundary at 3, at +3. Because we have a square bracket, the real numbers include that value of +3, but are everything less than that. So this is all real numbers such that x is less than or equal to +3. Now you try to graph the following infinite interval. and write its set notation. Now what you should get is a graph. Let's say this is the value of 4. Since we have a parentheses at 4, the value 4 is not included, and the number line extends all the way to positive infinity. You can describe this interval being all real numbers x such that x is greater than 4. Now let's talk about combining intervals. Just like with finite sets that we talked about at the beginning, we can also perform union and intersection operations with intervals. Now let's say we have two intervals. Interval 1 will be an open interval, 1, 4. Interval 2 will be a closed interval, 3, 6. Now let's find their intersection, or where they overlap. Now it's best to do this by drawing out the graph of each one. Here is interval 1. Interval 1 does not include the value at 1 and does not include the value at 4 either, but it's everything in between. Interval 2 includes the value at 3 and the value at 6, as well as everything in between. Now we can see exactly what they have in common. What they share begins at 3 and ends at 4. So I can draw out a new interval of their intersection, or what they share. They only share all real numbers beginning at 3, but not including 4. That is where they overlap. So from this, I can write the union of the open interval 1, 4 with the closed interval 3, 6 is equal to the half open, half closed interval starting at 3 and ending at 4. Now let's talk about their union, which is everything combined. What does that equal to? Well, if I want to include everything, I know that it starts at 1. And let's draw one more. So I know it starts at 1, the beginning here, and it ends here at 6. At 1, it's an open circle, so that value is not included. And at 6, it's a closed circle, so the value is included. So the union, the combination of the two sets, is a half closed, half open interval. It's open at 1 and closed at 6. It's just like with finite sets, but now we're dealing with a whole continuous range of real numbers. Now it's your turn. Your example is, find the intersection and union of the intervals -5, 2, closed, and the open interval 0, 7. Now it's best to think about these intervals on a number line, so we're going to start with that. So the closed interval -5, 2 includes the values at -5 and -2 and everything in between. And the second interval, the open interval, does not include the value at 0 and does not include the value at 7, but everything, all real numbers in between. I'm sorry. The first interval is all the way to +2. I made the mistake of just putting it at -2. Let's first talk about the intersection. So the intersection of the closed interval and the open interval is what they have in common. And what they have in common starts at 0 and ends at 2. At 0, the point is not included for the second interval, so I need to write that with a parenthesis. And the 2 is included, so we use a bracket. Now the union of these two intervals is everything that they share. And so what they share begins at -5 and ends at +7. -5 is included, but the +7 is not, so we use a parenthesis for that. To wrap up, here's what we learned today. A set is a collection of elements written with braces or set builder notation. We learned that this symbol means is an element or is in the set, and this means is not in the set. We learned about unions that combine sets, and we learned about intersections, which is just about showing overlap. We learned that intervals are sets of numbers shown using parentheses for excluded endpoints and square brackets for included endpoints. We learned that open intervals exclude endpoints and have no smallest or largest number within them. And lastly, we learned that infinity means the set extends without bound, and it is always used with parentheses. If you found this video helpful, please like the video and consider subscribing so you can follow along with my series. And if you want to practice what we've learned today or in any other of my videos in the Precalculus series, I've created a printable homework and quiz PDF for those lessons. You can grab it from my Gumroad page, linked in the description. It comes with an answer key so that way you can check your work. Thank you for spending some time with me, and I will see you in the next lesson.